Simultaneous inferences. Okay, so sometimes we want to be able to make several confidence intervals at the same time, and we want to be able to make a statement like, we can be 95% confident that all of these intervals contain the respective parameters. Well, a simple, naive, and incorrect way to do that would be just to make all the intervals at the same confidence level. You can't do that, okay? You can't do that because it turns out that the individual error, or the family error rate, will be inflated. So here's what you want to do. If let's say maybe we want this, we'll call this thing here in question the family confidence level. Okay, so maybe let's come over here to the side. So the family confidence level, we'll say, is this 1 minus alpha f. Okay. Now, there's something called the Bonferroni inequality, which you will actually prove in homework. I'll give you a big, fat, hairy hint on that, and do that by, say, prove by mathematical induction. Okay. The Bonferroni inequality says that if you have any events of interest, E1, E2, up through En, then the chance that all of these events occur is at least the sum of the chances of the individual events minus the number of them plus 1. Okay? And that's what we can use here. So let's let E sub I denote the event. If we want to apply this to our case here of making confidence intervals, let E sub I be the event that the ith random interval contains the ith parameter of interest. Okay, so if I'm interested in this probability of all of them containing their parameters of interest, let's let this probability here be 1 minus alpha f, sort of our family confidence level. This inequality, if I apply it to this case with confidence level intervals, I've got greater than or equal to, have the sum of these individual probabilities. Well, okay, so let's let each one of these confidence levels or probabilities be 1 minus alpha, okay? And let's let each one of them be that. So instead of just summing this n times, we've got n times that, okay? Minus n plus 1. Okay, so and all of this turns out to be, this is just 1 minus n times alpha, where alpha is, you could think of this as the individual type 1 error rate, okay, if you were just making one confidence interval. So for example, if we have this used car case, and maybe we want to make a confidence interval for the slope and a confidence interval for the intercept at the same time, and we want to be, we want to make some kind of statement like, hey, we're about 98% confident that this interval contains the slope, and at the same time, this interval over here contains the intercept. Okay, then here's what you do. You just take 98%, okay, and set that equal to n is the number of intervals you're making, which is 2 times 1 minus alpha minus 2 plus 1. Okay, and I'm going to solve for this. Okay, this will be my sort of individual confidence level. Okay, and when I do that, I see that 1 minus alpha turns out to be 99%. Okay, so then I can go through and I can use R to just make individual confidence intervals each at the 99% level. Okay, so I have in R here, I've got some things that we've already done. I've got my ages of the cars and the prices, and I've gone ahead and I've redone and found the slope of the regression line, the intercept of the regression line. I've got them here. Found the fits and the residuals, and the error sum of squares and the mean sum of squares. Okay, so here I've got the standard deviation for B1 and the standard error for B naught. Okay, so what I want to do is get this left and right, the left and right endpoints for these confidence intervals. So this one, so first I'll do for B1, but I'm making a 99% confidence interval, right? So that means that t-score should be at the 99.5 percentile, right? I've got 8 degrees of freedom, right? N minus 2, 10 equals n. So that'll be my left endpoint, and I'll do the same kind of thing to get my right endpoint. Okay, so it's exactly as it was before. The only thing we've changed is this number in here. Okay, and then I can get my left and right endpoint similarly for B naught. Okay, see how I've done that exactly as it is before. Best guess point estimator B naught plus or minus the t number times the standard deviation for B naught. Okay, see that, and then so I can actually get the interval, the intervals here. I just say B1 left endpoint is this. B1 right endpoint is this. B naught, my left endpoint for B naught is there. My left endpoint for my right endpoint, excuse me, for B naught is right there. Okay, so now what I can say is, now even though these are individually, they're 99% confidence intervals, the family error rate is 2%, right? So the family confidence level is 98%. So I can be 98% confident, I can be 98% confident that the actual value for B1 falls between these numbers, and the actual value for B naught falls between these two numbers right here. Let's try another example. Suppose we want to make simultaneous Bonferroni confidence intervals for the expected sales prices for these ages, 5 different ages. We want to make 5 different confidence intervals, but oh, you know what? There's no family confidence level stipulated here. Let's say the family confidence level is 95%, or you might hear it. You might say instead that the family error rate, the family type 1 error rate, is 5%. Okay, then just take 95% equals 5 times 1 minus alpha. So you're going to solve for this. You're going to solve for 1 minus alpha minus 5 plus 1. And let's see. This implies that what? 1 minus alpha equals 0.95 plus 5 minus 1 over 5. That comes out to be 0.99. Okay? So now what you'll do is you'll just use the procedure from the notes and make 5 confidence intervals for the expected sales prices, each one of those at the 99% level. Then you can make a statement that says, you know, we can be 95% confident that all of these intervals contain the actual mean sales prices. So now what I'm going to do is similar to what we did before. I'm going to say, you know, maybe I'll make a data frame for my price and age like this, okay, well, maybe data's already attached there. I've got, I'm going to run the linear model for data, store the output in something, I'll just call it out. This time, however, when I what I'm going to do, I'm going to call ND. I'm going to assign a data frame to ND, ND standing for new data. Okay. Say the idea is maybe you want to make confidence intervals based on for x values of these numbers, or by x values I mean age values. So when age equals 4, I want to make a confidence interval for the mean price or the expected price, and also when the age is 5, also when the age is 6. I want to do make these 5 confidence intervals at the same time. And in this case, we said we want a family confidence level of 95%, right? And we worked out then that meant that we could make individual confidence intervals, but each at the 99% level. Okay, so the level is 99%. And we can use that predict function to do that. Just stipulate that the interval is a confidence type. Okay, confidence type, not a prediction. And you can see the ND here. Okay, and what it's going to do is it's going to predict the mean response based on these explanatory variable values. Okay. All right. So, and of course, it's using the regression line from here, this linear model output that we stored in out. Okay, and press enter, and bang, there we go. We can be 95%. It says 99%, but remember this is the individual confidence level. So we can be 95% confident that the mean response when the age is 4 falls between here, and the mean response when the age is 5 falls in here, and the mean response when the age is 6 falls here, and so forth and so on. Okay, remember that these numbers have units of $100 bills. Okay, $100 bills attached to these numbers here. I've got 5 confidence intervals. Here's one right here. Here's one right here. Here's one right here. Here and here. Okay.